This is lesson 1 of rotational kinematics, or angular kinematics. We're going to use those words interchangeably. Angular, or rotational kinematics, is the study of the motion of objects spinning about an axis. So what things spin about an axis? So we've got planets, wheels, Beyblades, a record, like we looked at with the record player. So if we imagine something on a circle and moving, we want to describe that motion. So the circular path that it takes has a given radius, and it starts at some angle, theta 0, which we'll call 0 often, and then as it moves, we can describe the motion of an object on a rotating thing in terms of its angular displacement, the delta theta that it sweeps out. And an important point is that along the radial line, all points here have the same delta theta. So they're going to move the same amount of angular displacement in the same time. So they're going to have the same angular displacement. They're going to have the same angular velocity, which is just angular displacement divided by time, just like our linear velocity was displacement divided by time as well. And they'll have the same angular acceleration, the change in angular velocity divided by time. So physics describes the angular velocity with this vector, or with this symbol omega, and it is a vector, and the positive direction is counterclockwise. I think that's on the next slide. And we'll call angular acceleration the Greek letter alpha, which looks like a little fish. So angular displacement is how much an object has spun about the axis, and it is positive if the object moved counterclockwise. We're going to describe the angular displacement and angular velocity and angular acceleration with a base unit of radians. So we can describe how much an object moves along a circle in terms of revolutions, radians, or degrees. But the base unit that we're interested in is a radian, which technically isn't a unit, which is kind of strange, but I like to write it because it's going to help us do some analysis that will solve problems. So 1 revolution is 360 degrees, or 2 pi radians. And the definition of a radian is if I have a circle with a given radius, and I put that radius along the outside of the circle, or along the circular path, the angle measure that that distance sweeps out along the circle is a radian. So if we want to convert between units, if we have a record completing, let's say, 5 revolutions, and we want to determine its angular displacement in radians, we would take 5 revolutions and just multiply by the number of radians for 1 revolution, which is 2 pi radians. So we would get 10 pi radians, which you're welcome to leave as 10 pi, or 31.4 radians. So linear and angular motion are very similar, or rotational motion. So in linear motion, if we moved with a constant velocity, we would have a dot diagram that looked like this. And with rotational motion, if we move at a constant velocity in a circle, we'd have a dot diagram like this. And the position along the circular path would be x, and we can convert from linear position to angular position by just multiplying the angular position by the number of meters in 1 radian, which is the radius. That's the definition. So the radius is the number of meters per radian. So it's kind of the key to connect the two. So angular velocity is equal to linear velocity divided by radians. So if we have something in meters and we want it in radians, we would divide by the number of meters in 1 radian, which is the radius. So thinking back to our motion equations, for linear motion we had these great big 3 kinematics equations, and for rotational motion these equations are the same, but instead of linear displacement we have angular displacement, instead of linear velocity we have angular velocity, instead of linear acceleration we have angular acceleration. So these top two are in your reference table separately from the linear motion equation. I don't know why this last one isn't in your reference table, but it still works if you find it useful. Similarly, our motion graphs can be interpreted in the same way. So if we have angular displacement versus time graph, we can find the angular velocity from its slope. If we have an angular velocity versus time graph, we can find the angular displacement from its area, and we can find the angular acceleration from its slope. So let's do an example. A grinding wheel is initially at rest, is rotated with a constant angular acceleration of 5 radians per second squared for 8 seconds. So we can think of our understanding of motion and say, well, if we're finding the final angular speed of the wheel after 8 seconds, and it increased its angular speed by 5 radians per second every second, which is our definition of angular acceleration, then you should get 40 radians per second as its final angular velocity. Let's see how that works in some equations. The final angular velocity equals the initial angular velocity, or just the angular velocity. The angular velocity equals the initial angular velocity plus the angular acceleration times time. So we get 0 plus 8 times 40 radians per second. The wheel is then brought to rest with a uniform negative acceleration in 10 revolutions. What is the angular acceleration needed to bring the wheel to rest? So the angular displacement is 10 revolutions, which is 20 pi radians. And the initial angular velocity is now the 40 radians per second that we found before. And it's going to stop. And we're looking for the angular, looking for the angular acceleration. So this looks like one where we'll use that third equation, which doesn't have time in it. So we'll say omega squared equals omega initial squared, or the angular initial velocity squared is 2 times alpha times delta theta, the angular displacement. So we've got 0 squared equals 40 squared plus 2 times alpha times 20 pi. So it looks like we'll have alpha equal 40 squared divided by 2 times 20 pi. So that is just 40 times 40 divided by 40 times pi. So it's 40 over pi. Radians per second squared. So there's a nice simple example for us to start with, and we'll do another one in